second part of the session. So it's my pleasure to introduce Professor Longzhi Lin from UC Santa Cruz. And today he's going to talk about star-shaped mean conversion flow. Thank you.
All right, thanks. First of all, let me thank Jose and the town for the invitation and the arrangement. My first time here, seems quite interesting to see several friends here. All right, so today I'm going to talk about a recent work on the star-shaped mean curvature flow. So I'm going to assume, well, I guess some of you guys are expert in geometric flows, and I'm going to assume several of you are not familiar with mean curvature flow, and going to introduce some background material. And after that, I'll state the main result, and if we have time, then I'll get into some details, but hopefully not too much. So a family of smooth, let me assume smooth closed hypersurfaces, MT. So closed means compact without boundary. So the family of smooth closed hypersurface moved by mean curvature flow if at every point of the hypersurface, the hypersurface is moving in the direction of the mean curvature vector. So in this case, it will be minus mean curvature times the normal direction. That's our normal. So the simplest case of the mean curvature flow is for the one-dimensional mean curvature flow in the planar domain, in say, two-dimensional Euclidean space. Usually it's referred to as the curve sheltering flow. So intuitively, at a point where the curve is actually concave, then it's moving outwards. At a point where it's convex, it's actually moving inwards. So in some sense, the curve itself is actually moving into the shape, becoming more convex in some sense. So in 1987, Grayson proved that if you start with any embedded closed curve in the planar domain, then no matter what shape of the initial curve is, it would become convex in finite time and eventually shrink to a round point, combined with the earlier result of Gage and Hamilton, where they proved that if you start with a strictly convex planar curve, closed curve, then it shrinks to a round point. So you see in a movie made by Angelin that if you're starting with a very closed curve, winding around very much, it still becomes convex in finite time. And then once it becomes convex, then it shrinks to a round point. Okay, so that's the one-dimensional case. It's relatively well understood in this case. So in a high-dimensional case, instead of talking about the dense functional, well, the curve sheltering flow decrease the dense functional most rapidly. You talk about the area functional in high dimension. And the mean curvature flow really is just the natural negative L2 gradient flow for the area functional. So if you take the time derivative of the area functional along the mean curvature flow, you will get minus of the integral of the mean curvature square, which is always non-positive. So you see that the area is actually decreasing or non-increasing along the mean curvature flow. So the stationary solution to the mean curvature flow will correspond to the hypersurface where the mean curvature vanished at every point, where we commonly refer to as the minimum surface. So, of course, the flow will be, nature will be used to find minimum surface if you fix a, say, Dirichlet boundary, right? If the flow converge. But the bad thing is that almost every mean curvature flow develops singularities. So we got to know what kind of singularity occurs and try to understand the singularities. So as we see, the mean curvature flow is actually a flow on the space of hypersurfaces. You can think about that as the directional derivative of the area functional on the space of hypersurfaces. So it's moved by the surface tension to reduce the surface area. It first arose in material science, where people try to use the mean curvature flow to model the surface, the shape of the surface, the change of the shape of the surface when in a melting metal, for example, when the temperature is really high. So it's a nonlinear heat equation. So it has a short-time smoothing property. But Even you start with a rough surface, it will become smooth immediately. But the long-time behavior of the flow then is dominated by, sorry, there should be a square root in the divergence. So the long-time behavior of the flow will be dominated by the linearity. And we'll see in a minute that every compact mean curvature flow must develop singularities. So there's no way you can avoid singularities. So it's actually key to understand what kind of singularity would occur along the flow, even you start with a generic, say, compact initial hypersurfaces. So the simplest singularity that would occur is the so-called spherical singularity. If you take the simplest initial hypersurface as the sphere of some fixed radius, then since the sphere remains symmetric along the mean curvature flow, right? You move in the direction of the outward normal. So it stays symmetric. Then the mean curvature flow simply reduced to a ODE for the radius of the changing radius. So you see that the derivative of the radius equals to minus of n divided by r, because the principal curvature is 1 over r, and you sum them over, you get n divided by r. So you can solve the ODE, and the radius along time is equals to square root of the initial radius square minus 2nt. So after finite time, say t equals to r squared, r naught squared divided by 2n, it becomes distinct, right? So this is the commonly referred as the spherical singularities. But of course, there are many other singularities could occur along the flow. The second common singularity, which is commonly referred as the cylindrical singularities. If you take a dumbbell with two ends as the large sphere connected by a really thin neck, then along the mean curvature flow, the sphere, of course, the two sphere will shrink to a round point in finite time. But before that, the thin neck would shrink to a straight line in finite time, much less than the big spheres. So if you magnify along the neck where the singularity occurs, then you get a cylinder. Okay, so that's the cylindrical singularities. But then, of course, besides the spherical singularity and cylindrical singularity, there are much more exotic singularities, for example, that people nowadays try to use the gluing technique to construct singularity models. So I'm going to talk about it in a minute. So as I said, singularities are unavoidable, right? So this is simply coming from the comparison principle that we see for the PDE that's satisfied by the mean curvature flow. So if you take a compact initial hypersurface and enclose it by a large sphere, but we know that the distance between the two hypersurfaces is actually non-decreasing along the flow if you run the flow simultaneously for the two initial hypersurfaces. But for the sphere, it will shrink to a round point in finite time, but then the inside mean curvature flow will stay apart from the sphere. So before the sphere become distinct, the original mean curvature flow should develop singularities, right? Even before the sphere shrink to a round point. But then what singularity could occur for the original the inside mean curvature flow, right? That's the question. It could be spherical, it could be cylindrical, it could be even more complicated singularities. So it's actually quite crucial to understand what kind of singularity could occur for the flow. So the first fundamental result was due to Huisken in 1984, where he proved that if you start with a strictly convex initial hypersurface, what means strictly convex means every point of the hypersurface, the principal curvature is strictly positive. Then if you run the mean curvature flow, then you actually become convex and shrink to a round point. And this kind of behavior is quite analog it's really analog to the one-dimensional case, where Gage and Hamilton proved that if you start with a strictly convex curve in the planar domain, it shrinks to a round point, right? But the analysis here relies heavily on the fact that the initial hypersurface is actually strictly convex, so that you can apply the maximum principle for tensors, for example. But without the convexity, the strict convexity, there's really not too much you can say about the flow if you cannot use the fact that it's actually strictly convex. So the singularity analysis, I guess, relies heavily on the following formula, which nowadays commonly referred to as Huysken's monotonicity formula. So if you take the backward Higgs kernel of the n-dimensional Euclidean space, then integrate it over the moving hypersurface, and then take the time derivative of that functional, then you get minus of this square of this quantity times the backward Higgs kernel. And you see that this is actually non-negative. It's actually non-positive. So it's actually decreasing along the flow. So this is also parabolic rescaling invariant. So if you do a parabolic rescaling, it's still valid. So this monotonicity formula gives a really natural way to kind of define, kind of see how the singularity looks like if you do a parabolic rescaling. If you just take a microscope and look at a point where the singularity occurs, then magnify right along different scale, then what can you see? If the functional is actually stationary, then you see that it should satisfy this second order elliptic PDE, well, commonly we refer to as the self-shrinker. This is actually, if this mean curvature flow satisfies this equation, then it's a self-similar solution. And the minus one slice of that self-similar solution is referred to as the self-shrinker. So to understand this kind of functional, you can think about, for example, the backward Higgs kernel really is something that focus, converts to a point. For example, the mass or the energy actually concentrate at a point. So when the singularity develops, it's natural to see actually if the mean curvature flow develops a singularity, the area actually concentrates to a point. So along the backward Higgs kernel, if the area concentrates to a point, then it should develop a singularity. And this is also used, for example, in another geometric flow, for example, the harmonic mass heat flow, where people try to model the singularity for harmonic mass heat flow, where they just simply take the backward Higgs kernel for the Euclidean space, and then multiply by the energy density and take a look at the time derivative of that functional, and it's actually monotone along the harmonic mass heat flow. And that will give you an equation, second order equation, to model the singularity for the harmonic mass heat flow. So that's simply, I guess, most natural way to think about this kind of developing the development of the singularities. So so as I said, if the self-similar solution, well, if you take a parabolic rescaling, the rescale flow will still be a mean curvature flow. If we satisfy this PDE, then it's referred to as the self-shrinking solution, and it's the minus one slice of this. The minus one slice would refer to as the self-shrinker. So this is a second order PDE satisfied by the hypersurface. So people nowadays try to construct solutions to this PDE, which is a solution like a singularity model for the mean curvature flow. But the problem is that I guess the most interesting question will be, besides constructing the self-shrinkers, a more interesting question is that if you can, besides constructing the self-shrinker, can you construct a mean curvature flow that actually developed the singularity as the self-shrinker that you constructed? Otherwise, I guess all the extorted singularities or extorted self-shrinkers, they are highly unstable. So it might be possible that all the self-shrinkers that you constructed for this PDE would never occur in nature, right? So, So it's crucial to actually try to see what kind of singularity or what kind of self-shrinker you could get if you start with a generic initial hypersurface. So classification. At least, can you classify the self-shrinkers that arise from the broad limit of a compact embedded hypersurface? Right? That will be sufficient, at least for applications. So in a one-dimensional case, as I said, it's relatively well understood. Ambrest and Langer in '86, they proved that the only smooth, complete embedded self-shrinking curves which satisfy the previous PDE, where the mean curvature was replaced by the geodesic curvature, right, for one-dimensional curve. So they classify all the possible curves for that equation, and they said if it's embedded, complete, and smooth, then it has to be nice or circle. So that coincides with the previous result of Gage and Grayson, which says that if you start with an embedded curve, then it has to be shrinking to a round circle, right? If it's a 9, then the flow is actually smooth, doesn't develop singularities. In fact, they prove much more. Not only just the embedded ones, they actually classify all possible immersed self-shrinking curves for the curve shortening flow. So in a higher dimensional case, people would also like to classify the possible embedded self-shrinkers. So for type 1 singularities, Huisken in 96, using the monotonicity formula, he says that if you blow up, then you get a self-shrinker, right? So how do you classify possible self-shrinkers? He assumed that, well, if the self-shrinker is smooth, complete, embedded without boundary, with polynomial growth, so all these conditions are natural along the blow-up procedure, so that's not a problem. And additionally, he assumed that the self-shrinker is mean convex. Then he can also assume that the second Fraenkel form is bounded. That's also natural from the blow-up procedure. Then he proved that there must be the generalized cylinders or sphere. Okay, and later on, coding and ecology remove the assumption on the boundedness of the second Fraenkel form. Okay, so this is the sort of the starting point of the classification of the self-shrinkers, where you assume the mean convexity, right? So that you can say something about the classifications. So for type 2, the only result that is known so far, I guess it's due to Hamilton. Well, I should also mention before that the coding ecology also proved that if along one sequence of the blow-up, you get a generalized cylinder, then along every sequence you get the same cylinder. So that's the uniqueness of the tangent flow. So if it's a generalized cylinder, then you know it's always the same cylinder. So for type 2, Hamilton used the so-called essential blow-up sequence to get a so-called eternal solution for type 2 singularities. And he proved that if the eternal solution is also convex, then you get a Harnack estimate for the mean curvature flow. And from there, he see that if the convex eternal solution has to be strictly convex translating solutions. But again, that's only for one spatial blow-up sequence, which is the Hamilton's essential blow-up sequence. How about other sequence, right? What can you get? So the problem for the type 2 singularity is that the way you use the microscope to look at the singularity, you don't know how fast you should rescale, or how fast, what is the rate you should look at the singularities, right? So different weight or different scale might give you, a different sequence of scale might give you a different singularity. So that's essentially the problem. So once you know it's convex, and then Hamilton blow up give you an eternal solution, you know it's translating. Otherwise, it's not. So it's actually still widely open subject for type 2 singularities. So as we can see, the convexity here plays an important role in the classification. Right? Either the type 1 or type 2, it always relies on some sort of convexity, right? So that you can say something about the singularities. Right. So in a higher dimensional case, people try to understand the mean curvature flow starting with a very special initial hypersurface without convexity. Well, I guess the next natural assumption on the convexity will be mean convex instead of strictly convex, right? So during the last 15 years, Huisken, Charlie, and Brown-White has a series of important works that they prove that if you start with a mean convex initial hypersurface and run the mean curvature flow, then the blow up of the mean curvature flow at every point has to be convex. Okay? So using that convexity, now you can actually see that all the possible self-shrinkers has to be the generalized cylinder, right? So let's go back to the Huysken's classification, where we assume the mean convexity of the self-shrinker. But then, if you start with the mean convex mean closure flow, you can say more about it, because the singularity is actually convex, not just mean convex, right? So you have a classification. And recently, Haushofer and Kleiner used Benandro non-collapsing result to give a new proof of this result. You can actually see that the mean convex mean closure flow develop convex singularities. Okay, and Xu Jiawang also has some work on the classification of the convex translating solutions. Okay, on the other direction, without assuming convexity, say strictly convexity or mean convexity, Knut Mozik in '98, he studied the mean closure flow starting with star-shaped initial hypersurfaces. So star-shape means the support function, the position vector, that our normal is positive. So the star-shaped initial hypersurface. Then he proved that if you blow up at a point of the star-shaped mean closure flow, then the limit flow or blow up has non-negative scalar curvature. Okay, so that's essentially a pinching estimate along the mean closure flow. So he proved that that kind of pinching is preserved along the blow up procedure. So once you know that the limit flow has non-negative scalar curvature, then you can actually say something about the blow-up limit. For example, in 2 dimensions, if you know the scalar curvature is positive, then it will give you the convexity of the blow-up, right? Because the scalar curvature will dominate the principal curvatures. It will give you the sign of the principal curvatures. So in 2 dimensions, with this result, you can actually say, if you start with a star-shaped initial hypersurface, in 3-dimensional Euclidean space, then the blow-up limits are convex, just like the mean convex case. Then you know all the singular models. The self-shrinker has to be generalized cylinder or sphere, right? But how about higher dimension? What can you say about it? But in higher dimension, bigger or equal to 3, the scalar curvature doesn't give you any sign on the principal curvature, right? So you can only say the blow-up limit in higher dimension would have non-negative scalar curvature. That's it, right? But you don't have any classifications. So we want to know whether you can do it in higher dimension, right? So how about higher dimension? So we're going to prove here is that in all dimension, the blow-up limit of the star-shaped mean closure flow are convex, just like the mean convex case. So that you have a classification of all possible singularities. Okay, so of course the classification of the singularity will be important in terms of the geometry and topology applications. Well, if you know how the singularity looks like, how they develop, then you should be able, you should be able to look at the neighborhood of the space-time neighborhood of the singularity and do some surgery and continue the flow. But so far, I guess the only possible way, possible setting so far is, I guess, is the so-called 2 convex mean closure flow. 2 convex means if you add up 2 principal curvatures, it's always positive. So the way of the 2 convex mean closure flow is that if you can classify the singularities, and if it's also, additionally, it's also 2 convex, then the singularity type or the generalized cylinder are very limited. So it only split a line. So it's much simpler in a sense that you can actually work with it. If the singularity looks like something cross R square or R2, then it's impossible that you can say how would you do the surgery. So there's a series of work. I guess Huysken Senior in '09, they proved that they define a mean closure flow with surgery for 2 convex initial hypersurfaces in dimension bigger or equal to 3. And then Brandel and Huysken defined the mean closure flow with surgery for mean convex surface in R3. So that complete the story of the 2 convex mean closure flow in all dimensions. And then Haushofer and Kleiner gave a new proof of this. And then coding and Minkowski has a survey, I guess pedestrian, they have a survey on the mean closure flow, how to use the mean closure flow to treat the fault manifolds as a hypersurface in 5-dimensional Euclidean space. But that's a survey paper. Right. So the goal of the result that we wanna prove is to develop a structure theory for the star-shaped mean curvature flow without assuming any convexity. For example, strict convexity or mean convexity. Okay. And the star-shapedness of the initial hypersurface, in some sense, it's much easier to check than the mean convexity, for example, because the support function is only one order derivatives, and the mean curvature is actually second order. And geometrically, intuitively, it's much easier to check the star-shapedness of the mean curvature flow. But again, I should also point out that the way you can classify the singularities is that you assume much more on the initial hypersurface. So that's two kind of very special class of initial hypersurface that you can work on. But still, the geometry assumptions seem to be also very strong in the sense that the blow-up limits are all convex, right? But to classify the singularities, you only need the mean convexity, not strictly convex. But of course, this will give you very concrete examples or very concrete class of initial hypersurface that you can actually classify singularities. But that's, in general, it's impossible. So, right, so recently, Coding and College, they are developing a series for the generic mean curvature flow. That's a different kind of approach to this kind of whole story. Right, so we're gonna prove this so-called local curvature estimates and convexity estimates and blow-up analysis. That's sort of analog to the mean convex mean curvature flow theory. And then once you have the classification for the singularity, you can have a partial regularity result. And then, in fact, later on, we prove that all the analysis works for the smooth case, would work for the weak solutions, so that the convexity estimate or local curvature estimate not just work for the first-time singularity, but it actually works beyond the first-time singularity. So it actually works for arbitrary singularities, and that's by the elliptic regularization of Evans-Spark. Okay, so let me, in order to state the result, let me introduce some notations. So the quantity f over here is defined as the support function, the position vector that with our normal plus 2t times h. Then if you look at this quantity along the flow, you can derive the evolution equation for this quantity, and this looks very much similar to the evolution equation for the mean curvature. If you replace f by mean curvature, then it's still the same evolution equation. Then you see that if the quantity f is strictly positive, then by maximum principle, it will stay strictly positive along the flow. Okay, so for a star-shaped initial hypersurface, the quantity f is actually positive initially when t equals to 0, right? So it actually says that this quantity stays positive along the flow, but it might not stay star-shaped because this quantity might become negative and this quantity become positive, for example, right? So you don't see the mean convexity or star-shapedness from the PDE. So we're going to define the so-called alpha non-collapse flow. Right, so if instead of looking at the hypersurface, you can look at the n+1 dimensional region enclosed by the closed hypersurface. That's what we call K. Okay, so the hypersurface would be the boundary of K. So if a hypersurface is actually alpha non-collapse, then at every point of the hypersurface, it actually emits an interior and exterior sphere tangent at a point of radius at least a universal constant divided by the quantity f at the point P. But remember, along the flow, this quantity f is changing along time, right? So it's a t variable. So if the mean curvature flow, let's say Kt, satisfies the alpha non-collapse condition for every t, then we say it's an alpha non-collapse flow. Okay? So intuitively, the picture looks like this. The boundary of the region satisfies the alpha non-collapse condition if at this point it emits two spheres with a radius at least alpha divided by f. So, right, so in order to see this kind of condition, let me explain a little bit how do you use this kind of conditions. if you have a manifold, say, amidst the say, exterior ball condition, right, at this point, say, at a point X, on the hypersurface, amidst the exterior sphere condition or ball condition, then let's say this radius is R, and this point, let's say this point, the center of this ball is actually X plus R times mu. Mu is actually our normal, right, at a point. Okay? So in order to emit the exterior sphere condition, then for every point on the hypersurface, the distance of this point to the center of this ball has to be bigger than R for every point, every other point on the hypersurface, which says that y minus x plus R mu, the distance of this has to be bigger or equals to R for every point. Let's say this is N, right? Then it actually will emit a exterior ball condition, right? So then if you take the square of this, then you will see that this is equivalent to, say, y minus x. So if you take a square, then that's the square minus 2r, y minus x times mu, bigger or equals to 0, right? This is all equivalent. So then you see that this is actually equivalent to, say, 1 over r is, let's say, bigger or equals to 2 y minus x times mu divided by y minus x squared. So this is for every y other than x. And then you see that the radius r is actually at least alpha divided by f, right? So you have this. This is f divided by alpha, right? So if you look at this quantity, that's how you motivate to see, to look at this quantity, define the z, right, for every t and x and y. So then you see that the exterior ball condition and exterior ball condition would equivalent to, say, the z star, upper star or lower star, right? Take the in for soup. I guess in this case, we'll take the soup of that, right? That would be the z upper star. It's less or equals to 1 over alpha, right? Then it will satisfy the exterior sphere condition. And the other way is the same, right? So you just have to prove that this kind of condition is preserved along the flow, right? As long as you can prove it. So it's an important work of Ben Andrew in 2012. He proved that the z lower star and upper star satisfy this differential inequality, which is quite similar to the equation for the mean curvature and the second Fermat form. And they generalize this kind of differential inequality to a much larger so-called nonlinear curvature flow. And it also satisfies this kind of equation. So once you do that, you combine with the evolution equation for the quantity f, then you see that the quantity z star divided by f and z upper star divided by f satisfy the differential inequality, right? And then by maximum principle, as long as initially it satisfies that kind of exterior ball condition, then it will satisfy for the whole flow. But since it's star-shaped initially, so this quantity, this kind of estimate would hold for at least some alpha, then it actually says that the alpha non-collapse condition is preserved along the flow for the same alpha once initially set. Okay? So this kind of geometry condition, or exterior ball condition, or interior ball condition, would actually give you much more information at the region where the singularity occurred, because it actually prevents many different complicated situations to happen, right? So it has to be simple in some sense if you have this kind of geometric conditions. Okay. Right. So that's what I mentioned just now. That there's a generalization. So you can still talk about a non-collapsing condition for a more general class of geometric flows. So using this kind of non-collapsing condition, we can prove the following so-called local curvature estimates, which is analog to the mean convex case. So we prove that if you have at every point of the mean curvature flow, as long as it's actually defined in a parabolic ball, then as long as you have the control on the mean curvature, then you have the control on all covariant derivatives of the second fundamental form. So a mean curvature at a point will control the whole space-time neighborhood of the flow. So, and a natural corollary of this is that the gradient estimates for the second for the mean curvature flow, the covariant derivative of the second fundamental form is less or equals to a constant times the mean curvature square. So that's also needed in the mean convex case, as Huisken and Signor-Chari prove. Now, let's try to understand this local curvature estimate a little bit more. First of all, the curvature control, if the mean curvature is uniform bounded, then you give a regular point because all the covariant derivatives are uniform bounded, right, by the uniform constant. You can also now pass to smooth limit, assuming the mean curvature control at a point, right? Then if you have a sequence of mean curvature flow defined in the same space-time neighborhood, then you can pass to a limit to get a smooth limit since you have a uniform control. And this is also can be considered as the local harmonic inequality, which tell you that all the nearby points have the same curvature, right, for the mean curvature flow, if you start with a star-shaped initial hypersurfaces. Right. So, and then from here, once you have the local curvature estimates, then you can actually prove the so-called convexity estimate. So once you have a control of some scale of the mean curvature at a point, then the lowest principal curvature would be almost positive. So it's bigger or equals to minus an arbitrary constant times the scale of the mean curvature. So once you do a blow-up, for example, at the scale of the mean curvature, then you see that the blow-up limit has to be convex. Okay? So once you have the convexity of the blow-up limit, then you can classify the singularities using Huisken's result, just like the mean convex case. Okay? So that's essentially how it works. All right. So that's the corollary of this. Once you have the control on the mean curvature, then you have the control on the ratios of the lowest principal curvature divided by the mean curvature. It's almost positive. Right. Then, so from here also, you see that if you start with a star-shaped hypersurface for the mean curvature flow, then every special limit flow has non-negative second fundamental form. Okay? So that's essentially coming from the convexity estimates. So in the mean convex case, Huisken, Signor-Chari, and Brown-White, they also proved similar results, although the Huisken, Signor-Chari is more of a PD approach using Moser iterations, and Brown-White is more of a geometric major theory approach. All right, and then so Brown-White also proved this first of all with some restriction on the dimension and up to first-time singularity. And recently, there's a paper just published by Brown-White. I guess he has the result a long time ago. So using the elliptic regularization, he proved that all these estimates was for arbitrary singularity, not just the first-time singularity. All right. So here's the blow-up theorem. If you blow up at a scale of the mean curvature, then since by the local curvature estimates, then you see that you have the smooth convergence. If you do a parabolic rescaling, you have a smooth convergence, and it actually converges to a mean convex alpha non-collapse flow. So for the mean convex alpha non-collapse flow, the Haushofer and Kiner already has some classification or some structure theory for the mean convex, say, ancient flow. So they prove that for the alpha non-collapse ancient flow that is actually mean convex, then it actually has a convex time slice. For every time slice, it has to be convex. So that's coming from the convexity estimates. And you actually swipe out all the space. Okay, so that's the blow up. So if you fix a point and look at a tangent flow, then you expect to get a self-shrinkers, right? So using the convexity estimates, you see that if you do a parabolic rescaling, then you also have a smooth convergence. And the limit, which is a self-shrinker, since it's convex, then it's either, in the regular case, it's a static half space, or a self-shrinking round sphere or generalized cylinders. So that's a classification of the singularities, just like the mean convex case. So, right, so that's the tangent flows. And as I mentioned before, recently, coding mycology proved that the tangent flow has to be unique as cylindrical singularities. So in the case of star-shaped mean-curvature flow, you can see that all the tangent flow are unique, right? Because once you have the classification of the singularities for the star-shaped mean-curvature flow, then combined with coding mycology result, you see that the tangent flow are all unique. Okay. Right, so once you have a classification, you can say that if you start with a star-shaped initial hypersurface, then the singular set of the parabolic Hausdorff dimension of the singular set is at most n-1. Okay, so that's for the star-shaped mean-curvature flow. And also recently, coding mycology proved that the singular set for the mean-curvature flow with only cylindrical singularity, which means they are sphere or generalized cylinders, then the singular set, they have a better description of the singular set. So then, as you can see from the classification of the star-shaped mean-curvature flow singularities, their result also apply to the singular set. So you have a better description. All right? Right. So I guess I'm running out of time. I'm going to just say this. So we proved that the star-shaped mean-curvature flow would only have cylindrical singularities. Right. So I'm going to skip this. Using elliptic regularizations, you can prove all the estimates, all the result holds beyond first-time singularities. So using Evans-Sparks elliptic regularization. Okay, so right. So I guess right. Right. So final remark. I guess not just for the star-shaped initial hypersurface. If you start with something like a combination of the support function and the mean curvature, as long as it's positive, it's already pointed out by Smolzik and actually Huisken that they stay positive. And then the alpha non-collapsing condition would hold for along the flow. So with the kind of a little bit smarter choice of the rescaling, you should get the similar result as we did. So I guess I should also point out that the difficulty of the star-shaped mean-curvature flow is that you don't see the star-shapedness is preserved or mean convexity is preserved. It's not like the mean convex mean-curvature flow. You have the shrinking intuition where the mean curvature is positive, so the flow is sort of shrinking, right? But for the star-shape, some part of it might moving outwards and some part of it moving inwards. So we don't have the shrinking behavior. So we have to do a clever rescaling to see that the rescale flow is actually shrinking, and then coming back and forth from the original flow and rescale flow, and look at the estimates. Okay, so I'll stop here. Thanks.